CTE Training and Learning Academies 1 week faculty development program on smart cities. I, Indrani Borkar, on the behalf of Department of Civil Engineering, Government Engineering College Bilaspur, welcome you all in the second day's first session. I am overjoyed to take the opportunity to introduce our resource person of this session, Dr. P. Pravin Kumar Venkatrao. At present, he is working as an assistant professor in Earthquake Engineering Research Center, IIIT, Hyderabad, since December 2020. He obtained a PhD degree from IIT Roorkee in 2019. He has a 3 years of work experience in industry and research. He has recently awarded with Promising Young Structural Engineer Award 2020 by Indian Association of Structural Engineers for developing the cost-effective and sustainable retrofitting techniques for safety of existing masonry buildings. He is also a recipient of National Postdoctoral Fellowship by SERV India in 2020 and his Government Excellence Research Scholarship in the year 2017. Has been awarded with several national level awards for his excellence in the academics and research. He has published 22 research articles in various international peer-reviewed conferences and book chapters. He possesses numerous professional memberships and also the reviewer of several international journals. His research areas include seismic design of masonry buildings, strengthening and retrofitting of masonry building, displacement-based modeling, experimental testing and evaluation, etc. He will be addressing this session on topic strengthening of masonry structure of smart cities. Without further ado, I welcome Dr. P. Pravin Kumar Venkatrao. Please, sir.
Thank you so much, ma'am, for the very elaborated introduction. And a very good morning to Dr. Agarwal as well, and all
Good
the
morning, sir. Good morning.
participants of, yeah, to all the participants of today's event. And I would like to take this opportunity to thank the Professor and Head Department of Civil Engineering, Dr. Agarwal, and Mr. Aditya Singh for inviting me to deliver this e-expert talk. So if you allow me, sir, I would like to share my screen and we can go ahead.
Yeah.
Yeah, sure. And in
Indrani,
between, if the participants have any doubts or any query, then they can simply raise their hand so that I can stop my presentation and then we can discuss at any instant of time. There is no issue.
इंद्रानी सर को
Yes.
प्रेजेंटर बना दो.
Yes,
बना
sir.
दिए हैं. Yeah,
Yes.
she has. Yeah, ma'am, can you see the screen?
Yes, sir. Yes, sir. It is visible.
Yes.
Okay, fine, fine. So, today I'll be talking on the external flexural strengthening of masonry walls using the modern materials under seismic action. So, this is the brief outline of today's presentation. I will introduce you the topic first, and then we will discuss the seismic behavior of URM. URM means unreinforced masonry walls, their failure modes under the lateral loads due to seismic action, then how to improve their seismic performances and the strengthening methods. Then, in order to better understand, I will be discussing a complete case study where the comparative efficacy of different strengthening methods, which has been explored using experimental investigation and followed with the conclusions. So with this, let me introduce you the topic. See, we all know that since early civilization, if you see, the unreinforced masonry has been the most widely yes, the unreinforced masonry has been the most widely used construction technique all over the world. Even today, if you see, despite the extensive use of modern construction materials such as concrete and steel, unreinforced masonry still represents a great majority of building stock in the form of residential, institutional, commercial, and public buildings, which also includes the historical monuments and heritage structures of national importance, and which has been constructed all over the globe using this unreinforced masonry. In India, if you see the local available materials such as clay bricks, adobe, stone units, concrete units, compressed stabilized earthen blocks, even the autoclaved aerated concrete blocks are most commonly used for the unreinforced masonry construction. Okay, this masonry basically refers to a very vast spectrum of structural constituent materials and systems. When I'm saying masonry, it is basically a composite material which is usually developed by using the units, that is, it may be a bricks or blocks, and the another material, the binding agent, will be a mortar. Okay, so this is basically created by using the sand, water, and the binding agent. And this binding agent may be lime, mud, or cement. Okay, so by the combination or the amalgam or the mixture of unit and mortar together basically creates a assembly which we called as a masonry, right? It may be brick masonry, it may be stone masonry, depending upon what type of units which we are using, especially for the construction. Now, in order to join or to connect two units together, we need a binder, and you need this particular binder especially at the bed joint or the head joint we are referring to. Now, here I want to clear that we are not looking at mortar especially as a render element. Render element means which is a plaster, but more as a material that can be used for the bed joint or the head joint mortar. So here it is a combination of, as I said, sand, water, and binder. Now, when you are dealing with masonry without any reinforcement, then it is called as URM construction, unreinforced masonry construction, where there is no reinforcement at all. Okay, no external strengthening techniques has been used. It is simply without any reinforcement, which is made up of units and the mortar. But on the other hand, there is a confined masonry or there is a reinforced masonry where this vertical reinforcement and the horizontal reinforcement has been used. So these reinforcements are typically embedded either in the mortar or in the ground. But here the question arises is that why URM is so popular? This masonry is very popular owing to its advantages, such as it is very simplistic in construction, easiness in future alterations, the usability of locally available materials, less skilled and relatively lower labor cost, and thermal comfort. But despite these advantages and very strong in compression, a significant issue with unreinforced masonry construction is that having a low tensile strength of the masonry. And because of this low tensile strength of the masonry, the unreinforced masonry usually have a brittle nature of failure. We will see in the consequent slides what are the failure modes. And because of this low tensile strength of masonry, which makes the URM building susceptible to sudden and fragile failure to certain modes when subjected to the seismic forces. Now, let me give a statistics. Now, if you see, as per the 2001 and 2011 data of housing, if you see the 2001 and the 2011 census government of India, and if you see the total number of or the total percentage of the buildings which has been constructed using the different materials such as burnt brick, stone, mud or unburnt brick, if you add all these three numbers, okay, then you will get almost 75 to 76 percentage. Similarly, in the 2011 census, 24, 14, and almost 48. So you can see that almost 76 percentage of the existing building material, existing building stock present in India, it contributes to masonry structures, and nearly 44 percentage of masonry walls have been constructed using this burnt bricks, and the remaining 32 to 35 percentage have been made either of mud, or basically these are the unburnt bricks. So thus over half of India's population, if you see, they lives in unreinforced masonry houses. Although there is a trend of not constructing these buildings no more, even if the unreinforced masonry buildings are being constructed, either they are made up of confined masonry or reinforced masonry or with these special connections. But the existing building stock is so much that their vulnerability we need to assess, and we need to safeguard all these structures, which basically occupies the most percentage in terms of the building stock. If you see, almost 76, and remaining 24 percentage is only left with the concrete structures or with the steel structures. So the performance of these URM buildings during the past earthquakes in India, I want to take you to the previous slide. Now, if you see these two graphs, here you can see that the performance of URM buildings during past earthquakes in India and around the world is very poor, and contributed to the major part in threat to the life safety. And therefore, the collapse of masonry buildings became the primary cause for the loss of life during an earthquake. So you can see that lot of fatality has been occurred. And as I said, that because of this brittle nature of unreinforced masonry, it is liable to fail. And that became a major reason for the threat to the life safety and the collapse during the lateral forces. Now, if you see majority of these constructions made up of burnt bricks, stone masonry, or the unburnt bricks, if you look at a country like India, where 60 to 70 percentage of our landmass is sitting in seismic zone 3, 4, and 5, okay, which are called as moderate to high seismic zones. And if you look at these structures, most of them will not have any seismic resistant feature, okay, and the earthquake resistance of this existing masonry construction in India is notoriously very poor, and therefore this type of construction is usually regarded as non-engineered construction. So in a country like ours, the earthquake protection or the risk reduction in earthquakes are of predominant majority of the population living in such constructions is really a big challenge. And therefore, the existing housing stock of residential buildings, you can see from these building census data, which are constructed out of masonry with almost no earthquake resistant features, is really a worrying situation. Now, if you see this masonry buildings, the main component, this is basically a load bearing structure. Let me tell you the basic difference between a load bearing structure and the frame structure. In the frame structure, usually we basically construct the beams and the column framework. And there, all the masonry walls are considered as an infill wall, or they basically act as a partition. And there, in that particular case, the load is basically being transferred from the upper floors to the beams, from beams to the columns, and columns to the foundation. Okay, where this masonry wall, which is constructed as an infill material, does not contribute to any strength participation. Whereas in case of load has to be borne by the wall. I think it has stuck somewhere. Okay. Yeah, as I was saying that the actual behavior of an unreinforced masonry wall, if you see during an earthquake, is a complex combination of in-plane action and out-of-plane action. I will be explaining you this. Now, if you see during an earthquake, what exactly happens to a masonry building? During an earthquake, this unreinforced masonry walls, they may be either pushed sideways along their length or basically the thickness direction. Okay. And therefore, if you see, the moment of inertia is a very good geometrical parameter that captures the bending strength. Now you just imagine if there is a wall, and if I take the bending about its x-axis, then if you calculate the moment of inertia, it comes out to be around T times thickness into L cube by 12. But if you take the same moment of inertia about the y-axis, therefore it is around LT cube by 12. Now, if you take a ratio, the bending strength about these two axes, then you can see that the IXX is almost 170 times more than the IYY. Considering an example of length of the wall as 3 meters and the thickness of wall is 230 mm. Therefore, this in-plane resistance, if you see, the in-plane resistance of the wall is significantly very larger because the depth of plane of bending in this axis, if you see, it is quite larger. So here you can see that a person is getting lot of difficulty in pushing this wall about this axis. Whereas this action is called as in-plane action. When the seismic forces or the lateral forces acts in the direction of the plane of the wall, then it is called as in-plane action. And the failure associated to it is called as in-plane failures. Whereas if the direction of the lateral forces are perpendicular to the plane of the wall, then it will be much more easier because the failure usually occurs. Here you can see the failure usually occurs about the bed joints, and the joints are mainly the main plane weakness of the planes. Okay, so the joints are the your weak planes, and because of that it's much more easier to overturn or to fail this wall in the out of plane direction. So what do you think? So if you see that when the masonry wall is subjected to in-plane lateral forces and when it is subjected to out-of-plane forces, so which one do you think is more resistance? The in-plane walls are much more resistant to seismic forces, whereas on the other hand, the out-of-plane forces are much more dangerous because these walls are vulnerable, especially in this direction. Now, after stating this, let me explain you the complete phenomena of what is in-plane failure. See, what actually happens is during an earthquake, the earthquake may act in X direction, it may be in Y direction, or it may be along some vertical frequencies always there. But if you see about X and Y axis, then when a wall is shaken along their length, okay, so let's see, this red arrow is basically showing my direction of an earthquake. So this wall, when it is shaken along their length, the wall will offer much greater resistance. Why? Because of its large depth in their plane of bending. And this action is called as in-plane action. It has been observed in the past earthquakes that if the masonry wall is subjected to such in-plane forces, then this diagonal X-shaped cracks in the wall originate especially from the corners of the openings. See, these are two peculiar pictures from the Bhuj earthquake, and where you can see that these diagonal X-shaped cracks are basically occurring and originating from the corners of the openings. And this in-plane failure also depends on your aspect ratio. And what is aspect ratio? Aspect ratio is basically the ratio of height to the length of the wall. Okay. And this in-plane failure also depends upon your wall thickness, what is the compressive strength of your masonry as a material, and what is the axial stress. Okay, what is the pre-compression load, which is basically coming from the top stories. So considering all this, the development of the shear or the flexural stresses beyond the ultimate limit can cause this in-plane failures, right? And the aspect ratio, that is height to the length of the wall, also has a significant influence, especially on the failure mode of the walls. The low aspect ratio generate the shear failures, while the high aspect ratio values lead to the flexural behavior of the walls. Now here you can see that this in-plane failure modes are classified as the rocking. The rocking means it governs the response, especially at the low level of vertical stress and the high aspect ratio. Okay, so when the pre-compression load, which is coming from the top, is very less, and the wall is having a very high aspect ratio, that height to length ratio, then this type of failure is usually happening. Now, second is the toe crushing. In toe crushing, what happens when the level of vertical stress is very high and the aspect ratio is also very high, then this type of toe crushing failure takes place. And the third is the bed joint sliding. It occurs at a low level of vertical stress and at a low aspect ratio. And last is the diagonal tension, which is the most common failure mode, especially you can observe when there is a wall which is basically subjected to an in-plane lateral forces, is the diagonal tension, which corresponds to a very high level of vertical stress and especially the low aspect ratio. So this is all about the in-plane failure. Now, what is out of plane failure? What happens is, now, as I said, when the shaking or when the direction of the lateral forces are along their thickness direction, then the wall simply collapses. Why? As the seismic resistance of the wall, by virtue of its weight and tensile strength of masonry, as it is very, very small. As it is very, very small. Now, if you see that this out of plane failure is classified into two types. One is called as one-way spanning walls and another is called as the two-way spanning walls. So in case of one-way spanning, here you can see that it undergoes uniaxial bending. Just hold for a second. Yeah, sorry for the inconvenience. So as I was saying that when the shaking is along with their thickness direction, the wall simply collapse as the seismic resistance of the wall, by virtue of its weight and the tensile strength of masonry, as it is very, very small. And here this out of plane failure is classified into two types. It may be a one-way bending, it may be a two-way bending, depending upon what is my boundary condition. Okay, which I will be explaining it to you when I come to the case studies, how we are defining the one-way bending and how we are defining the two-way bending conditions. But at the moment, you simply understand that this one-way and two-way bending is associated to the boundary conditions. Okay. Now, in one-way spanning walls, you can see that it may undergo uniaxial bending. Okay. Therefore, it develops the cracks parallel to the bending axis. It may be a horizontal bending or it may be a vertical bending. Whereas in case of the two-way bending, if you see that it will undergo biaxial bending, okay, which causing a more complex failure mechanism that includes the horizontal cracks, the vertical stresses, at the especially at the interface. Interface means it is a surface or a plane which basically lies between the unit and the brick unit and the mortar joint, that I'm calling it as an interface. So at the interface, it creating a combination of horizontal, vertical and the diagonal crack patterns. Okay. walls have especially failed in the, so all the walls, especially in the out of plane failure, has been failed. So whether you take an example of a Latour or Kutch earthquake or the Bhuj earthquake or the Nepal earthquake, here you can see all the walls, when the earthquake or the lateral force is in the direction which is perpendicular to the plane of the wall cannot resist that particular force. That is because failure patterns. Here you can see that all the failure patterns that the masonry walls have been subjected to the out of plane failures. Now let's move forward. Now, these lateral forces which we have seen that it acts in plane direction or basically in out of plane direction. Now, there is also a effect of the diaphragm. In simple words, the diaphragm is nothing but the roof. Okay, the diaphragm is basically nothing but the roof or basically the floors. Now, what happens is the seismic lateral forces basically originate in all the components of these structures, right? So it will be subjected to the vertical elements, that is my masonry walls, and second is my horizontal components, which is basically the roof. And this component, there are basically two types of a diaphragm. So one is basically a rigid diaphragm or another is basically the flexible diaphragm. The example of a rigid diaphragm is basically an RCC slab, reinforced cement concrete slab. And the best example of a flexible diaphragm is basically a sloping roof or pitched roof, which is basically not properly anchored to the masonry wall. And therefore, it is flexible in nature. Now, let us discuss few points about the rigid diaphragm condition. Now, as I said, if your masonry walls are supporting an RCC slab which is properly connected to this masonry wall where the construction has been done in situ, in that connection, in that sense, all the lateral forces will be transferred first to the rigid diaphragm and through connections. And this diaphragm then distribute the inertia force to the different elements of the structure. Okay, but it based on relative stiffness. Therefore, this in-plane rigidity of the floor or the roof to act as a horizontal diaphragm as shown in the figure is very, very crucial. And when I say the in-plane stiffness, it is being much higher than the out-of-plane stiffness, right? As I told you, the moment of inertia about Ixx, which is TL cube by 12, and the moment of inertia about y-axis, which is LT cube by 12. So because of the large depth in the plane of the bending, the in-plane resistance is quite high. Similarly, this in-plane stiffness of the masonry walls are much higher than the out-of-plane stiffness. And because of this feature, the wall resists the lateral loads primarily through in-plane action. Okay. And the out-of-plane inertial forces developing in the walls are being transmitted to the diaphragms, either above and below, and then to these in-plane masonry walls. Therefore, an adequate anchorage, okay, anchorage means the connection between your vertical elements, that is my masonry wall, and my horizontal elements, which is in this case an RCC slab, needs to be properly connected together. And this adequate anchorage between this diaphragm and this vertical resisting elements is essential for the satisfactory transfer of the inertial forces. And as I said, the roofs and floors which are very stiff in nature, flat, and which is attached to this masonry using good quality mortar have got a beneficial impact on the performance of masonry buildings during earthquakes. Now, on the other hand, if you take the case of flexible diaphragm, as I said, it may be a sloping roof, floor with tiles on the joist. Okay, it may be a flat roof, but without any proper connection. So without any proper anchorage comes under the classification of flexible diaphragm. The buildings which are having flexible diaphragms, they are subjected to more damage. Just take you to this picture. If you see Nepal earthquake, this is my sloping roof. Here also you can see that this is my sloping roof. Here also at the top, if you see, it is a sloping roof. Here also in the Bhuj earthquake. So the sloping roof is subjected to much more damage because of the lack of anchorage connection. And for that, the out of plane failure is considered as a governing failure mode in those cases. Okay, so as I said, they are subjected to more damage. Why? Due to this out of plane failure of the walls. Okay, and if they are not supported by external ties or seismic bands or belts, therefore in the case of flexible roof building, the only mode, especially for transfer of out of plane inertia force, is the horizontal flow to especially the cross walls through corners, and the corners are basically the first to damage. Okay, especially in the freestanding walls. Why I'm saying freestanding wall? If the connection between your roof and the wall is not proper, then these walls simply act as a cantilever walls, and cantilever walls are also called as the freestanding walls. So they result in freestanding walls susceptible to out of plane failure. Not only that, if my diaphragm length is very large, so the long span diaphragm can also undergo excessive in-plane failures, horizontal deformations, which are leading to cracking and the collapse of masonry walls. And hence, the anchorage between the diaphragm and the wall must be capable of transferring this in-plane shear forces from the diaphragm to the masonry walls and must be capable of providing support to the walls in out of plane action. And inadequate anchorage of roof diaphragm into the masonry wall can cause first loss of support, and therefore it results in the out of plane bending of walls as cantilevers, leading to their failure, which in turn results in complete collapse, as you can see in the Nepal earthquake, in case of the Bhuj earthquake, right? So now let's understand what are the different causes of failures. We have already seen, let's understand in much more detail. If you see this horizontal inertia forces, which is developed at the roof, transfer to the walls, acting either in the weak direction or the strong direction. Here I want to define, when I'm saying weak direction, it is basically the direction which is perpendicular to the plane of the wall. Let's say if this is my direction of earthquake shaking, and this force is basically perpendicular to the plane of wall B, that this direction is called as my weak direction or the out of plane direction. Whereas the same earthquake direction is parallel to the plane of the wall, and therefore the A wall is called as the strong wall or the in plane walls, because they are much more stronger than the wall B. Now, the another reason is, if all the walls, all the four walls, if they are not tied together like a box, then the walls loaded in their weaker direction, they must tend to overturn or topple. And therefore, to ensure the good seismic performance, therefore, to ensure the good seismic performance, it is very much necessary that all walls must be joined properly together to the adjacent walls. So in this way, what happens is, if the wall is loaded in the weaker direction, then the weak direction walls can take the advantage of the good lateral resistance offered by the walls, specially loaded in the stronger direction. And further, the walls also need to be tied to the roof and foundation to preserve its overall integrity. This is very important. And therefore, several construction aspects are required to ensure this complete box action. Okay. Now, secondly, the size. Firstly, as I said, the connection between the walls must be good. And how this can be achieved? This can be achieved by ensuring the good interlocking of the masonry courses, especially at the junctions. Secondly, employing the bands, okay, at the various levels, especially at the lintel level. And secondly, the sizes of the door and the window openings must be kept much smaller. Smaller the opening, larger is the resistance offered by the wall. And thirdly, if the wall is too long in comparison to its thickness, then it is particularly vulnerable to shaking in the weaker direction. And hence, there is a tendency of the wall to overturn when it is basically pushed in the weaker direction or out of plane direction. And that can be reduced by limiting its length to thickness or height to thickness ratios. And what are these ratios? This has already been mentioned in our Bureau of Indian Standard. If you go to IS 1905, Okay, this code came in 1995, and then in the year 2002, this has been reaffirmed again. And if you follow that code, then there are specific ratios which have been given. What will be the slenderness ratio? What will be the aspect ratio which we need to maintain in order to safeguard the masonry walls against the lateral forces? Now, how to improve the seismic performance? After understanding the different failure reasons, now one of the common technique which is used to safeguard the unreinforced masonry wall against out of plane seismic action is providing the lateral support in form of the bands, okay, at the intermediate level to reduce the vertical span. Okay, so this band, what it basically doing, which is provided at this lintel level, this band which is basically provided at the lintel level, what it is doing, it is basically reducing your unsupported height of the wall and thereby improving their stability, especially in the out of plane direction. This horizontal bands, if you see, they are the most important earthquake resistant feature in the masonry buildings. And these bands are provided to hold a masonry unit building as a single unit by tying all the walls together. Here you can see that this lintel band is basically tying all the walls together and create a support for the walls. And these bands may be provided at different levels. It may be at the lintel level, it may be at the sill level, it may be at the plinth level, and it may be at the gable level. But even if you can provide the lintel level, which are basically tying all the walls together, then we can assure the safety of the structure. Here I have given an example. You can see this particular building onto your left is the building with no lintel bands. And during an earthquake, you can see that the complete building has been collapsed. The roof has been collapsed. The walls have been collapsed. Whereas a building with lintel bands, here you can see that this white color band has been provided all around. And because of that, there is no damage in the structure. And therefore, especially for the new construction, if you are going for an unreinforced masonry, we had to understand that providing the horizontal bands is very, very important as far as the earthquake resistant features are concerned. Now, let's And one more thing I want to add here is that this gable band which you are seeing at the top, they are employed especially in the buildings with the pitched roofs or basically the sloped roofs. And this plinth bands which are basically can seen at the bottom, these are primarily used when there is a concern about the uneven settlement of the foundation. Okay, now even the question is that even if we provide the horizontal seismic bands, then can we will be assured that the safety of the structure is intact? The answer is no, because even if these horizontal bands are provided, the masonry buildings are weakened by the openings, okay, in their walls. So here you can see that the rocking of the masonry pier can basically crush the masonry at the corners. Otherwise, the piers are more likely to develop the X-type cracking, okay, and therefore embedding vertical reinforcement bars, especially at the edges of the wall piers, and anchoring them at the foundation level at the bottom and the roof band at the top is necessary. Here you can see that the vertical reinforcement bar in the edges of the wall pier forces this slender masonry piers to undergo bending instead of rocking. And therefore, in wider wall piers, this vertical bar enhances their capability to resist the horizontal earthquake forces and delay the X-type cracking. And further, this vertical reinforcement also protect the wall from sliding as well as from collapsing in the weaker direction. Now, till now, whatever measures, earthquake resistant features we have seen, it is with respect to a construction of a new unreinforced masonry building, providing the horizontal seismic band, okay, assuring the connection between the two walls together, providing with the rigid diaphragm, Okay, even providing this vertical reinforcement is only possible when there is a new construction. But what about the existing buildings which has already been constructed in the past? What about their safety? You cannot embed the vertical reinforcement externally. You cannot provide the lintel band separately. For that, some special arrangement needs to be done. And for that, the strengthening methods, external strengthening methods comes into picture. Okay, for especially for the safeguarding the existing buildings. Now, a number of strengthening techniques using composite materials or the modern materials have been evolved over the years to increase not only the in-plane but also the out-of-plane performances of the walls. In my case study, which I will be explaining you later, I have focused on the out-of-plane behavior, but the same thing can also be assured in case of the in-plane failures as well. Okay, so the main function why we are providing this external strengthening in order to enhance or in order to increase the in-plane and the out-of-plane performances of the wall. And these techniques which have been used in the past, if you see, they not only enhances the strength, but also their deformation capacity and the energy absorption capacity of the walls. So here you can see that a polyester fiber, this fiber may be made up of different type of fiber materials, like it may be a carbon fiber, it may be a glass fiber, it may be an aramid fiber, or it may be a natural fiber also, like basalt, hemp, sisal, cotton, jute, even you can use it. But these fibers are used as a chopped fibers. And the technique, the strengthening technique, when you are using this chopped fibers along with the cementitious matrix, then it is called as ECC. ECC means engineered cementitious composite material. Another is the post tensioning you can go for, or you can basically provide fiber ropes in order to prevent the out of plane failure. Even you can go with the textile reinforced mortar. I will be explaining you this in much more detail. This TRM, you simply remember that it is a fiber mesh. It is basically a bi-directional mesh with some openings, and this basically is attached to the masonry walls. And then externally, here you can see that a mason is basically applying a cementitious matrix in order to bind or in order to join my masonry wall with basically my reinforcement. Okay, the another may be polymetric nets, it may be FRP bars, it may be in form of fiber reinforced polymer strips, it may be a bands, or it may be a wire reinforced mortar. So there are different techniques which has been used in the past. Now, in the case study, we have developed a 3 effective and sustainable retrofitting techniques for unreinforced masonry buildings, especially for out-of-plane action. And if you see, these 3 innovative, sustainable, easy to apply, and cost-effective retrofitting techniques have been tested, and their efficacy is validated using experiments. Okay, now here the first technique, the first reinforcement which we have chosen is the welded wire mesh. Okay, this is a wire mesh, this is a fiber mesh, and another is the textile fabric. Okay, now if you see, this wire mesh and fiber mesh has been used in conjunction with the inorganic matrix. Okay, inorganic matrix means it may be a cement sand mortar, it may be a lime mortar, or it may be any cementitious matrix. Whereas in case of the textile, we have used a material called basalt, and in order to join this material to the masonry wall, we are using a binding agent called as organic matrix, which comes under the category of epoxy resins, and especially the epoxy hardeners have been used. Now, first we go to the testing of walls. We have tested the materials, especially we have tested all the materials, and then we have characterized at the component level, and then we will see in the structural level what are the tests have been done and what will be the strength difference when it is unreinforced and when there is a reinforced masonry. Then what is the strength enhancement, what is the deformation enhancement, what is the energy absorption capacity, that we will see in a while. Now, First, we have took some clay bricks, and the compressive strength and the elastic modulus of bricks have been basically tested. And we know, as I said, that this masonry is a combination of units and the mortar. So the bricks and the mortar and their mechanical properties, that's what I said, compressive strength and modulus of elasticity, are the factors governing the properties of masonry. And therefore, the masonry and its constituents have been tested. So the compressive strength of the brick has been determined using ASTM standard guidelines, using direct compression. And here you can see that the size, the nominal size of the brick of a non-modular brick, you can see that it is 9 inches by 4 inches by 3 inches, and the brick strength comes out to be almost 26 MPa. So we have tested almost 10 number of bricks, and the strength, the average strength what we got is 26 MPa, and the modulus of elasticity is in the range of 6000 MPa. Now, similarly, the mortar, which is the another important ingredient of the masonry. So we had chosen 1:4 proportion of the cement sand mortar. And let me add one thing. IS 4326 is a specific code which is to be used in conjunction with the IS 1893, which is a code for earthquake resistant design of structures. IS 4326 suggests that if you want to construct, or if there is an existing construction, or then in that particular case, and if the building is located in seismic zone 4 or 5, then the mortar which you need to use, either it needs to be 1:4 or needs to be 1:6. Okay, you cannot go beyond that. But practically speaking, that 1:6 mortar is a very lean mortar. Okay, the strength is comparatively very lesser. So the most important guideline is, if you want to construct any building, then the cement and mortar used should be either 1:4 or slightly higher than that, but not less than 1:6. And therefore, in this case study, we have chosen 1:4 cement and mortar. And therefore, we have prepared a 75 by 75 by 75 mm mortar cubes. And after 28 days of curing, then based on ASTMC 109 guidelines, we have tested under compression. And the masonry strength we got, the mortar strength we got here is 14.75 MPa, and the modulus of elasticity is 5266. And how this modulus of elasticity is calculated? It is simply the secant modulus. Okay, it is simply the secant modulus. We took 33% of the ultimate strength, and then we took a basically slope between 0 and the 33% of the compressive strength. So whatever value we got, the slope of that line will give you the modulus of elasticity, I'm referring it as a secant modulus. Now next is the masonry. As I said, masonry is an assembly of a unit and mortar together. Whereas in constituents, we have tested brick separately, mortar separately. Now let's understand what will be the behavior of masonry in assemblage. Now here you can see that the stress strain characteristics of brick masonry prism, which are determined under monotonic uniaxial compression in accordance with ASTM C1314. Now the majority of these prisms, okay, they basically failed in compression due to vertical splitting cracks. Okay, here you can see that the vertical splitting cracks either in the phase shell separation mode, whereas some of the prisms are also failed in semi-conical break and cone and split mode. So these failure modes have been defined as per the guidelines of ASTM. So in a layman's language, mostly the failures are associated are basically my vertical splitting cracks. Now, this ASTM standard classification identifying this local variation in the crack patterns and spalling in the different tested specimens, which indicates that the material is not homogeneous. It is basically an heterogeneous material, and there is a large variability in the material properties, especially in case of the masonry. So when we tested a masonry specimen of H/T ratio of 2.38, we got a compressive strength of 7 MPa, and the modulus of elasticity, it is in the range of 3375. Now let's see the summary. So we have tested 10 bricks, strength of 26 MPa, mortar cubes 14 MPa, prism around 7 MPa. Now it is usually said that the mortar strength should come in between the brick and the mortar cubes. But here you can see that the masonry prism strength is comparatively lesser than that of the brick unit and the mortar when it is a completely assemblage. So here we can see that the maximum strength of masonry prism, which is 7, is less than that of brick and mortar, which is contrary to the generally believed stress strain curve of masonry lying between brick and mortar. However, this type of behavior is not unexpected, let me tell you, in case of masonry, when it is constructed with very stiff bricks, very high strength bricks, and with the strong or intermediate mortar. Okay, which has also been observed by several researchers in the past for the similar case of the Indian masonry. Now, once this masonry properties we got, now about the reinforcement. I talked about 3 different type of reinforcement. One is the wire mesh, another is the fiber mesh, and another is basically a fiber textile. Now, let's understand the behavior of this reinforcement in tension, because why this tension reinforcement is required. As I said earlier, that the biggest disadvantage of masonry is that it is very, very weak in resisting the tensile strength. And in case of the concrete also, why we provide the steel reinforcement? The main reason to provide the steel reinforcement is to be more effective, especially in the tension zone, because concrete cannot take tensile forces. Even if it can take the tensile forces, it is in the order of 1/10 or 1/20th of its compressive strength. And therefore, we provide the steel reinforcement below the neutral axis. Similarly, in case of the masonry also, as it is very strong in compression, but it is equally weak in tension. Therefore, in order to enhance its tensile strength, we need to provide the external reinforcement, especially in the tension zone. Now, we have tested 3 different type of materials. So first is the bidirectional, this welded wire mesh. Here you can see, okay, of 2 grid spacing 25 mm and 50 mm. And second is the bidirectional basalt fiber mesh, okay, which are basically made up of your basalt fiber yarns in warp and weft directions with 2 different grid spacings. Now, if you see, according to AC 434 guidelines, this metal tabs, here you can see that the brown color metal tabs have been bonded on both sides of the specimen, especially in the gripping zone, using an epoxy glue. And this arrangement, what it does is, it basically avoids the damage to the specimen, especially by the hydraulic grips in the test machine, and improves the stress transfer mechanism at the reinforcement mortar interface. Okay. Now, what we do is, we basically first provide a first layer of plaster of maybe 5 to 6 mm, and then we basically provide this reinforcement as a sandwich material. Okay, that's why it is called as a composite matrix, or it is also called as the coupon specimens. So here we have provided the wire mesh as well as the fiber mesh, and then again we provided a second layer of plaster. Okay, and then the specimen has been cured for 28 days, and then after curing, they have been provided with these metal tabs. Okay, and the reason of providing the metal tabs, as I already mentioned, to avoid the damage of the specimen when you basically test in the universal tensile testing machine, because this hydraulic grips in the test machine may damage the specimen, and therefore this metal tabs are very, very important to provide in order to have the shear stress transfer in order to improve the stress transfer mechanism at the mortar reinforcement interface. And last is the fiber textile, which I said this has been used in conjunction. Here you can see this wire mesh and the fiber mesh has been used in conjunction with the inorganic matrix, that is cement sand mortar. Whereas in case of the FRP, fiber reinforced polymer composite, we have used the epoxy resin and the hardener. So similar type of specimens have also been provided. The only difference here is organic matrix rather than inorganic matrix. So a bidirectional fabric of 0.35 mm thickness has been used, and similarly the metal tabs have been anchored to the ends of the specimen. Now let's come to the test setup and the test results. Now in the present study, the clamp type grips have been provided to test the reinforcement and the composite specimens in the direct tension. And these tensile force has been applied using the specially designed grips in order to avoid any slippage. Okay, so this is my wire mesh specimen, fiber specimen, then the composite specimen, and then the FRP specimen. Now let's see the results. Now here you can see these are the test results of the welded wire mesh, fiber mesh. From the stress strain curves, you can see that the wire specimens of the welded wire mesh have shown a non-linear behavior, however, with much lower ductility in comparison to the structural steel and rebar, especially in case of the 25 wire mesh before the wires got ruptured. Okay. Now, the fiber yarns, if you see, the fiber yarns of a roving have also shown a linear stress strain curves and have got a brittle failure. Here in this curve, you can see, let me on the laser pointer. Here you can see that there is a sequential load drop and again the regain in the stress strain curve, especially for this basalt fiber mesh. Okay, so which are attributing, why this is happening? This is attributing to the progressive progressive breaking of the individual fibers or the yarns of a roving. And therefore, and the difference in the mechanical properties in the warp and weft direction is due to the influence of the weaving process. Okay. And if you see the FRP composite failure modes, the stress results of VFRP are quite repetitive and the stress strain curves are almost linear right up to the failure. Okay. Now next, if you see the test results, this tensile strength is basically obtained by dividing the load recorded by the cross-sectional area of the specimen. Okay, and in the present study, if you see that the tensile strength of this welded wire mesh obtained is observed in the range between 580 to 850 megapascal, whereas for basalt fiber mesh, the strength comes out to be in the order of 900 to 1200 MPa, and for the fiber reinforced polymer, the strength comes out to be 326 MPa. So this is all the test results of the dry fiber mesh, not of the composite. Now let's see for the composite specimens. Now in case of wire reinforced, this WRCM representing the wire reinforced cementitious matrix. So what is WRCM composite? This is the specimen, okay, where there is a wire mesh has been inserted between the two layers of my cement sand mortar plaster. Now here you can see that the cracks have been occurred along the width and have been distributed evenly in the full length of the specimen. But for a majority of these specimens, the failure has been caused because of the sequential breaking of the wires inside the cementitious matrix. But a very few specimens showed tensile failure of wires near the gripping area. So here you can see that the blue lines basically showing the test results of the dry reinforcement, whereas the red color stress strain curves or the load displacement curves are representing for the composite specimens. Here you can see that there is a reduction of 25% to 11% in strength in comparison with the dry wire reinforcement. Whereas if you see the initial stiffness, they are almost in a very close match. So this reduction in strength can be attributed to the sequential failure of the multiple wires present in the coupons. Okay. Now, let's talk about the same thing with the fiber reinforced cementitious matrix. So in case of FRCM composites here, you can see that in all the red curves compared to these blue curves, the slippage has been occurred by numerous cracking along the width, which has been distributed homogeneously over the entire specimen length. And the majority of the specimens have shown slippage between the mortar and basically the fiber mesh. And except for one specimen where the sequential rupture of the fiber yarns has been observed. And the slippage is mainly attributed to the low bond strength of the interface between the mortar and the fiber mesh. And therefore, there is a significant reduction in all the four stress strain curves. You can see there is a significant reduction in the strength and stiffness of FRCM coupons compared to the dry fiber yarn. And this reduction can be attributed to the gradual slippage of the fibers. Now we had talked about the compression behavior of the masonry and its constituents. We had talked about the tensile behavior of these composite materials as a dry reinforcement and as a composite material for the wire, fiber mesh, as well as for the FRP. Now let's apply the application of this strengthening reinforcement to the actual masonry. Okay, so for this we have constructed two different type of specimens. Okay, so this is all this the small specimens are usually called as wallets. WALLETTES. These are not walls, these are wallets which are having a small size specimens. So we know that the masonry properties are different in its orthogonal direction, and therefore if you see the flexural strength of masonry has been determined perpendicular to the bed joints as well as parallel to the bed joints. Now, here in case of the URM wallets, we have basically gone for the 3-point bending test, or you can say the 4-point bending test rather. And here we have constructed a test specimen, and then we have basically laid it horizontally without any compression load, and we have applied the loading in especially in flexure, especially in bending. And we wanted to see when we construct the specimen perpendicular to bed joint and when we construct the specimen parallel to the bed joint, so what is the orthogonal strength ratio we are getting? Okay, now in this particular test results, you can see that in URM wallets subjected to the bending tension perpendicular to the bed joint. See, when I'm saying perpendicular to the bed joint, the force, let me show you with a highlighter. See, when you apply the load, here the tensile forces will be developed about its bending axis. So this tensile force is basically perpendicular to that bed joint. Okay, whereas in this particular case, my bed joint is straight and the force is also acting parallel to that. That's why we are saying parallel to the bed joint. So here we are referring parallel and perpendicular with respect to the bending axis, not with respect to the plane of failure. So here you can see that in case of perpendicular to the bed joint, a sudden strength degradation and the brittle failure has been observed once the cracking has been initiated. But when the same wallet has been constructed parallel to the bed joint, it has been observed that the cracking is initiated in the head joints and propagated either in the toothed pattern, okay, along a combination of head joint and the bed joints. And why this has happened? This is due to the interlocking of the brick units. The strength degradation in the masonry wallets testing with bending tension parallel to bed joint was a little slower, and therefore the load carrying capacity has been increased. Here you can see that the average strength comes out to be 5 kilonewtons, near to 5. If you see the average of these four curves, the average comes out to be at a range of about 12.5 kilonewtons. And therefore, the load carrying capacity in parallel to bed joint is increased to about 2 to 2.3 times to that in case of bending tension perpendicular to the bed joint. Here it was a sudden failure where it was basically it's not a sudden failure, rather it is progressed with a toothed pattern along a combination of head and bed joints. Now, so this is all about the unreinforced masonry. Now, what we did is we had tested the same unreinforced masonry by retrofitting or strengthening by using the wire mesh. Here you can see that in between the different courses of the brick, we have applied our dowel bars. What we did is we applied a first layer of the mortar, then we applied this welded wire mesh as a layer, and then in order to join the masonry substrate and this wire mesh together, we have used these dowel bars. These dowel bars have been laid while constructing this masonry specimens, and once the mesh has been applied, these has been bent so that they have been integral action takes place. So for as far as the integrity of the substrate and basically the dowel bars is concerned, they has been tied, and then the second layer of plaster has been applied. So and then finally the specimen has been ready. Same thing has been done for perpendicular to bed joint. Okay, the construction of parallel to bed joint is the only difference, whereas the application of this welded wire mesh will remain same. Now, if you see the test results, we have tested the different types of specimens with the varying reinforcement ratio. Now, here you can see that for bending tension perpendicular to bed joints, they have been either failed in sliding shear along the bed joint, or because due to the diagonal shear cracks, which is basically joining the support and the loading line. Whereas some of these specimens which are strengthened with 50 mm wire mesh, here mostly the failure is associated to either flexure, or basically in some cases the sliding shear is also tested place. So here you can see that this shear failure, here the sliding shear and the diagonal crack patterns which you are seeing, they are mainly attributing to the fact that these are being tested in horizontal position without any axial force, and the low shear span to depth ratio, okay, is also responsible for this shear failure. See, the main intention is when we are testing these masonry specimen in bending, why this specimen failed in shear. In some of the cases here, you can see that there is a flexural failure, but in some cases the shear failure is occurring. The main reason is the low shear span ratio. Okay, so it is interesting to note that the flexural failure is brittle. If you see the the load displacement curves for the flexural failure, they are much more brittle, whereas the shear failure has got some ductility. So here it is also related to the how this strengthening reinforcement basically got failed. This brittle flexural failure is accompanied by the rupture of the wire mesh and can attribute it to a very low reinforcement ratio, resulting in very shallow depth of the neutral axis. Whereas on the other hand, in case of the shear failures, the gradual sliding has been registered by this catenary action of the welded wire mesh, which is resulting in slightly ductile failure. Now, in order to understand this failure modes better, we had tested few more specimens and then using the larger shear span. And now you can see with an increased shear span, with the same reinforcement ratio, now the failure mode has been changed from shear to flexure or flexural shear. See, here the reinforcement ratio is 0.144. Here also the reinforcement is basically 0.144. Here the failure pattern, if you see, either this is diagonal shear, cracking, or basically the sliding shear. Now here you can see that they have been converted into flexural failure. So by simply changing the shear span depth, the failure modes can be changed. But compared to the unreinforced masonry specimen, if you see, here the strength is 5 kilonewtons. Rather, in the welded wire mesh, the strength enhancement is almost 100 kilonewtons. Here also you can see that the strength enhancement is 120 to 140 kilonewton even. So just by adding 0.14 percentage of wire mesh, you can gain a tremendous increase in strength, tremendous increase in deformation, and the tremendous increase in energy absorption capacity. Here you can see the maximum displacement this specimen can take is almost 1 mm. In case of parallel to bed joint, it is about 2 to 2.5 mm. But especially for wire mesh, if you see the specimen, the maximum displacement have reached up to 25 mm. Here 20 mm. So the deformation capacity is also larger. And even the energy absorption capacity, which is if you take the area of the stress strain curve, that will give you the energy absorption capacity. That is been also tremendously increased. Now let's come to the basalt fiber mesh. So as I said that in case of the wire mesh, the similar technique we had applied. Okay, here also we have applied the first layer of plaster, then we had laid with the your basalt fiber mesh, and then again the second layer of plaster has been applied. And here, rather than double bar, a mechanical anchorages or the mechanical wall plugs has been used in order to join the masonry substrate and the strengthening reinforcement. And we have tested in 4-point bending test. Now, in this test also, you can see that all these specimens have failed in flexure. And here the intermittent drops. Here the intermittent drop and the strength gradients, which is basically indicated by the local peaks in the load versus displacement curve, is due to the sequential failure. Here you can see the failure patterns due to the sequential failure of individual fiber yarns and redistribution of tensile forces to intact the yarns are occurring. So the wallets ultimately failed because of the rupture of the fiber mesh. And however, the debonding of the fiber mesh from the masonry has not been observed. So apparently, the mechanical anchors are very, very helpful in the good bond of the basalt fiber reinforced cementitious matrix with the masonry. Here also, especially for perpendicular to bed joint, your unreinforced masonry somewhere lies here. It's around 5 kilonewtons. Now the strength enhancement is up to 40 kilonewton, you can see. Especially for the parallel to bed joints, you see, the strength enhancement was around 12 kilonewton, especially for URM, whereas the strength has increased almost to 32 to 35 kilonewtons, especially for the strengthened masonry. Now, let's take another strengthening technique. Here we have basically tested, here we have strengthened the unreinforced masonry by using the fiber reinforced polymer, FRP composites. See, as we know that the masonry surface is usually rough, very uneven. It's not at all smooth. For that, we have done the grinding. Then we have applied some cohesive agents, and then we have tested the different configurations of the FRP composites, which is indirectly indicating the increase in the reinforcement ratio. So here there is one strip, two, three in diagonals, and then the complete strip and the combination of horizontal and vertical strips. So here, rather than cement mortar or as a plaster, we have applied the epoxy resins. So what we did is we applied the first layer of the resin on especially on the top of the masonry substrate where you want to adhere your FRP strips, and then this takes then the second layer of epoxy resin has been applied, and it has been cured and left for almost 7 days under the normal atmospheric condition, so that this particular strips will basically adhere to the masonry surface and will basically gain its strength. Now, when this FRP specimens, when the specimens have been retrofitted using FRP, and now if you see their failure patterns, all the wallets which are basically strengthened using FRP, they also failed in bending. No shear failure has been observed. These are some of the test results for the different configurations of the FRP specimens with respect to the increasing reinforcement ratio for perpendicular to bed joint. Here you can see that the strength enhancement initially was 10 when you applied a 0.024 percentage of reinforcement, which is very small. Now, with increase in reinforcement ratio, you can see that the strength is also increasing. Similar trend you can also follow for the parallel to bed joint. Here the strength enhancement around this 24. Now when the reinforcement ratio is increased from 0.24 to 0.153 percentage, the maximum strength gained is almost near to 40 kilonewtons. But in FRP, three different type of failure modes has been observed. Either the FRP rupture has took place, which is attributed to relatively better bond characteristics. Second is basically due to the debonding. This is also a rupture failure. This is also a rupture failure. Here you can see that there is a debonding which is followed by the slippage of this FRP due to one of the edges of the wallets. Now, in addition, in few cases, there is a combined failure mode. In one case, there is a rupture, and in the second case, there is basically a debonding. And you can see that when there is a debonding, the full tensile strength of the material is not utilized. And therefore, in this case, you can see that the specimen with the debonding mode got a strength of around 30 kilonewton, and when the specimen basically failed in rupture, where the full tensile strength of the material has been utilized, and therefore the strength has almost gone to the double, almost it has reached to the 60 kilonewtons. So this FRP strengthening technique also shown a significant enhancement. Now, if you see this curve, see this bar charts, you can see that all these strengthening techniques have shown an enhancement, not only the flexural strength, but also these strengthening methods. See, here if you see on the y-axis, this is a ratio of the strengthened masonry to that of the unreinforced masonry. X-axis is basically showing the type of different strengthening techniques which has been applied in the present study, and also we have collected some of the test results and we have normalized it in order to have the better understanding. So this is the strength ratio. Similarly, this is the deformation ratio. So this is the deformation of the strengthened specimen to that of the deformation of the unreinforced masonry specimen. And next is the energy ratio. So few curves for perpendicular to bed joints, few bar charts for the parallel to bed joints. Now in all the cases, since it is the ratio which has been taken with respect to unreinforced masonry, you can see that the strength enhancement, if you see, they have been gone almost up to 16 times. If you use the wire mesh, you can see that the strength enhancement is almost 16 times. Whereas in case of a deformation, the deformation capacity is enhanced up to 24 times that of the unreinforced masonry specimen. In case of an energy, it is almost 240 times. Okay, the similar trend you can also observe for the parallel to bed joints, whereas there is a strength enhancement, there is a deformation enhancement, and where there is an energy enhancement. So, as I said, that these strengthening methods not only increased the flexural strength, but also enhance the deformability of the wallets before the failure, which allows to dissipate more energy, especially in case of the cyclic loading, especially in case of the earthquake loading. So as a result, but the thing is, as a result, the designer has the difficulty in choosing the most appropriate technique. And therefore, the selection of the technique depends upon the several factors. So for this, an effort has been taken to identify the relative efficacy of different techniques to help the designer to choose the most appropriate strengthening system. And for that, the strength ratio, deformation ratio, and energy ratio has been developed. Okay, so here you can see that, especially in case of the FRP composites, here you can see that there is a strength enhancement, but they are comparatively smaller. Why? Because in case of the FRP, the predominant failure mode is the debonding. And as I said that, here you can see that the carbon fiber has basically showing the highest strength, whereas the hemp fiber is showing the lesser strength, because the tensile strength capacity, if you compare, of these two composites are comparatively very small for the hemp basalt compared to that of the glass fiber and the carbon fiber. There is another important point which I need to address here, is that if you are using the low tensile strength composite like hemp, basalt, and flax, they are able to utilize the reinforcement to its full capacity. And the failure is basically occurring in case of the rupture. Whereas when the wallets are strengthened using very high tensile strength fabrics, then there is a problem especially related to the debonding failure mode. But here all the test results has been with respect to the rupture failure mode has been drawn, and therefore you can see that welded wire mesh is performing very well in case of the strength, whereas in case of the deformation you can see that the basalt fiber mesh BFM is basically providing the highest deformation ratio, whereas again in case of the energy dissipation capacity, the welded wire mesh is basically showing the highest gain in strength enhancement. So this is a low cost material and a very effective, not only in terms of the strength, but also in terms of the deformation capacity. So all these strengthening techniques have shown as a promising solution for the unreinforced masonry specimen and for the unreinforced masonry walls. Now, so this is all about the one-way bending test. Here you can see that all these specimens which I had showed, they has been basically tested in 4-point bending. Here you can see that there is no axial load, and therefore you are basically to move. and therefore this is a case of a one. Now, let's talk about the two-way bending. This is very important, the two-way bending condition. Now, to understand this behavior of masonry walls, especially in two-way bending, this H-shaped masonry wall, this is a full-scale wall where the length of the wall is 3 meters and the height of the wall is about 3 meters is constructed. This main wall and the cross walls have been interlocked at the junctions using these staggered overlapping bricks. Here you can see that the toothing connection has been developed. So as we tested for the one-way bending, 3 different types of specimens, and we have shown what is the strength and the deformability capacities. Now similar thing we had applied at the structural level, especially at the masonry walls, the 3 different techniques. One is the welded wire mesh, another is the basalt fiber mesh. So this is the welded wire mesh, another is the basalt fiber mesh, and another is the fiber reinforced polymer. Okay, so how we have applied, let's discuss this and then we will go to the results of that. Now in case of the welded wire mesh strengthening technique, the masonry wall has been retrofitted using wire mesh. Here you can see that there is a first layer of plaster which has been laid along the length of the wall. Okay, similar to that of the lintel band which we had discussed earlier, but the lintel band is usually provided especially for the new buildings. But for an existing building, we are basically externally providing these seismic belts. This is not a band, this is called as a seismic belts. Especially I have provided here at the lintel level. So there is a layer of a plaster, then there is basically a wire mesh, and then they have been connected using these dowel bars. Then again the second layer of plaster has been applied, and then this is a complete seismic belt which has been laid all around the wall, not only on the one face, but this is in continuation. So this is provided in continuation along all the perimeter of the walls. Okay. Now, this bandage, when we are providing this seismic belt or the bandage, this is provided continuously on both the faces of the wall, main wall as well as to the cross walls. And the dowel bars have been used to connect the masonry and this welded wire mesh to ensure a composite action or to transfer the shear forces at the interfaces. Now, this horizontal bandage, what it is doing is, it is integrating the orthogonal walls and support the main wall, especially in the out of plane direction. Okay, especially in the out of plane direction. Now, in case of the basalt fiber mesh strengthening technique, this fiber mesh is applied on full area on both the faces of the wall using the hand layer procedure. The fiber mesh has been placed and attached to this masonry wall using that mechanical anchors, the mechanical anchors which I had discussed earlier. This is my mechanical anchor which has been used specially for the fiber mesh. Now, in case of the FRP composites, the FRP has been applied on both the faces of the wall, similar to that of the welded wire mesh. Okay, but in form of an horizontal bandage at the lintel level, similar to that of the wire mesh, where we have provided a vertical bandage as well as the horizontal bandage. So the vertical bands or belts are specially called as the splints. Okay, vertical FRP which you are seeing, this is called as basically a splint, and the horizontal component of the strengthening reinforcement is specially called as the bandage. Here you can see that BFRP vertical splints and then the BFRP bandage. In welded wire mesh and the basalt fiber mesh, we have used the inorganic matrix, cement sand mortar, where in case of the FRP, we had applied this strengthening technique using the epoxy resin and the hardeners. Now here you can see that the test wall notations, here they are basically suffixed by a letter F and basically the S. What this F and S is indicating? This F and S is to indicate the boundary conditions, especially at the top edge of the wall and top edge of the wall. So the F is basically indicating the walls with integral support at the top, which is obtained by constructing an RCC slab by pouring the concrete directly over the wall. So this is representing my rigid diaphragm condition, which I had discussed earlier. Now, next case is the S. The suffix S is denoting the wall with the non-integral boundary condition, that is the precast. So where the RCC slab has already been constructed and it is simply supporting at the top of the wall, okay, simply over the green mortar layer on the wall top. So this is my representing the flexible diaphragm conditions. So we have used the different techniques as well as we have studied the effect of the diaphragm conditions on the wall as well. Now, let's me take you to another slide. Yes. Now, this is an important parameter for this two-way bending test. Why I'm saying here it as a two-way bending test, if you see the main wall, its vertical edges are being restrained by the cross walls and the top and the bottom is already restrained because the bottom is restrained by the floors, whereas the top is basically restrained by the hydraulic compression, the axial forces which we are basically providing at the top. So my all four ends are basically restrained, especially in case of the suffix F condition, that is my rigid diaphragm condition. Whereas in case of the flexible diaphragm, as I said, the connection between the roof and the wall is simply obtained by using a green mortar layer. So this is my representing flexible diaphragm, where my three edges, the vertical, two vertical edges and one bottom edge is basically under the fixed conditions, whereas the top edge is basically my non-restrained condition. Now here the question arises is that how to apply the realistic seismic forces in the out of plane direction in order to fail this particular wall in out of plane bending. Okay, so for that we had developed a unique test setup, okay, and where the loading has been applied using airbags. Okay, so here you can see that this is a reaction frame which is consisting of 4 columns which are connected by these steel beams, okay, in the loading direction, and there is a steel beam especially in the transverse direction, so 4 reaction frames, 2 steel beams in order to have provided in the loading direction, and the two steel beams which are basically provided in the transverse direction. All the members of this reaction frames have been connected using high strength friction grip bolts, and the columns have been connected to this concrete floor using these anchor bolts. Now here you can see that especially in the columns the stiffeners are provided, even in the beams the stiffeners are provided. So the main reason to provide is that all the points where the concentrated forces are acting. Now if you see the lateral movement of RCC slab at the top of the wall has been restrained using these 4 steel rods, okay, between the slab and the reaction frame, and this hydraulic jack has been used to apply a pre-compression load from the top. And to distribute the vertical load uniformly in the test wall, a steel beam has been attached to the top of the RCC wall along the length of the main wall. And this lateral load has been applied by using this S-type load cells, okay, which has been attached between this backing frame and the reaction frame at the 4 reaction points. And for the displacements have been measured using this 4 LVDTs. The 2 LVDTs at the front side of the wall and 2 LVDTs have been applied on the another 2 ends of the wall. And to minimize the leakage or due to the friction underneath the backing frame of the applied load, the backing frame has been supported on the rollers and the ball bearings. And the lateral load, the most important part, has been applied by using these airbags, okay. Using these airbags, so these are basically made up of polypropylene material, and this 6 number of airbags where the complete air is managed by this manifold with pressure gauges, okay. Through an air compressor the air will come inside this manifold, and here you can see that there are a number of pipes which are basically connected to this manifold, and these all the pipes are connected to these airbags. So once the air is passed on onto these airbags, these inflate and they basically apply a lateral load on this masonry wall, okay. Now so here you can see that here the salient feature of this test setup is that there is a provision of the application of pre-compression load. There is a provision of application of uniformly applied load. Here you can see this backing frame, and just beside this particular backing frame, there are 6 number of airbags have been applied. So this backing frame is basically placed very close to the wall so that the airbags will basically inflate and basically apply an uniform thrust in form of uniformly distributed force by means of an airbags to that masonry wall, so that the masonry wall will basically fail in the out of plane lateral direction. So here you can see that all the 5 walls which I said, one is the unreinforced masonry wall, second is the welded wire mesh wall with the S is basically suggesting your flexible diaphragm condition. Here it is the welded wire mesh with the rigid diaphragm condition. The basalt fiber mesh wall and the FRP wall are constructed with the rigid diaphragm condition. So these all 5 walls have been subjected to an identical quasi-static reversed cyclic. Here you can see the plan of the test setup, where this is my main wall, where this is my main wall. These are my 2 cross walls. These pink color are my airbags, which are connected to this backing frame. Okay, so since here you can see that in the time history, there is a to and fro action, and therefore in order to simulate the similar force, the to and fro action has been simulated in the real field. Okay, so where one push has been basically applied on the one side, and then this backing frame is basically taken to its initial position, and on the other side again a push will be given. So it's like a cyclic kind of a behavior, to and fro actions at the different intervals. So here you can see that the load has been applied to the wall in 2 phases. One is called as a pre-cracking phase, which is consisting of first half cycle of the load to the significant cracking of the wall, that is up to having a well-defined collapse mechanism. And second is the post-cracking phase, which is consisting of a reversed cyclic load with the displacement loading history. Okay. So this pre-cracking phase, which you can see with the help of blue colors, this pre-cracking push has been applied till a significant cracking is achieved. And once that significant cracking is achieved, then we are basically applying to and fro action of these airbags in order to develop this hysteretic curve. This pre-cracking phase representing a force controlled stage in which the pressure in the airbags are gradually increased till the wall depicts a clear cracking pattern to determine the pre-cracking strength. On the other hand, my post-cracking, the hysteretic loop, which are representing the cycles of different amplitudes which have been applied starting from the residual displacement to that of the pre-cracking phase. Now, here it can be observed from the figure that the load displacement behavior of all the wall has got 2 distinct phases. The strength during the pre-cracking phase is much higher, which is shown with blue color, which reduces drastically in the first cycle of the post-cracking, whereas the degradation in the successive cycles is relatively gradual in all the cases. Now, if you see, let's understand their crack patterns. Now, the crack patterns, if you see for all these 5 walls, it is very close to the idealized crack patterns. When I'm saying idealized crack patterns, I would like to take you to this old slide. Yes, can you see this one? So this is my case of two-way bending, okay, where my all 4 edges are basically restrained. So there will be a vertical cracks, there will be a combination of horizontal cracks along with the diagonal crack patterns, and they all are almost appearing near to the corners. So similarly, in case of the real test also, we had seen similar kind of a cracking patterns. However, in this case, the diagonal cracks did not originate directly from the corners of the test wall. Now, in case of this welded wire mesh wall, there are 2 cases, one with the rigid diaphragm, another with the flexible diaphragm. Here you can see that the cracks are developed parallel to the horizontal bandage, and the wall has divided into 2 distinct zones. See, this is my band, and all the cracks are occurring just beneath the band, whereas the top Okay, there are only the horizontal cracks. Here you can see that top photograph just above the band. Here you can see that there are no diagonal cracks, there are only the horizontal cracks you can observe. Whereas classical diagonal type crack patterns have been developed just beneath this welded wire mesh. Okay, so it means that in this case, the welded wire mesh has not ruptured. However, in case of welded wire mesh with the flexible diaphragm condition, a vertical crack has been propagated through the bandage and the reinforcement shown a clear picture. So in this particular condition, the wall has been distinctly divided into two different zones. Zone 1 at the top and zone 2 at the bottom, when you have provided the rigid diaphragm condition. But in case of the flexible diaphragm, it has behaved totally differently, where there is no strength enhancement. I will show you through the bar chart, through the graphs, that the strength enhancement in case of the flexible diaphragm is very less, even it is similar to that of the unreinforced masonry. Okay, because in case of the flexible diaphragm, as I said, there is a lack of anchorage connection. Now in case of the basalt fiber mesh, if you see, so the wall strengthened using basalt fiber mesh has developed its full capacity, and the failure showed the rupture of the fiber mesh. And here in case of the wall tested with the BFRP condition, especially at the top edge, the last course of the brick acted monolithically with the RCC slab during the out of plane bending. As a result, the horizontal cracks have been. Here you can see that all the test walls, see this with the suffix F, it means they all are representing my rigid diaphragm, and this is the only wall which is representing my free boundary resulting due to the precast construction, that is my flexible diaphragm. Here you can see that all the tested wall with the rigid diaphragm boundary condition or integral boundary, the last course of the brick is basically acted monolithically with the RCC slab during this out of plane loading. As a result, the horizontal cracks have developed one or two courses below the ceiling line. Whereas in case of the wall with the rigid flexible diaphragm condition, the RCC slab has been simply supported because the slab is directly resting over the top of the wall without any monolithical connection. And in this case, the sliding of the wall relative to the roof slab has been observed during the initial push itself. Okay, so this is the effect of the boundary condition. Now, here you can see that in all the retrofitted walls, see this black line is representing the envelope for the pre-cracking phase for the unreinforced masonry, and the other different colors are representing for the strengthened wall. This green color dotted line which you are seeing, this is for welded wire mesh. However, this is strengthened, but this is with the flexible diaphragm condition, and because of that there is hardly any strength increment. However, you can see that the stiffness is increased significantly, and this is for the post cracking phase. Now if you see all these graphs, there is a clear evidence of increasing pre-cracking strength and stiffness. See, here the unreinforced masonry strength is just around 170 kilonewtons. For wire mesh, the strength has increased. For fiber mesh, even for the FRP, the strength has increased. Not only the strength, similarly you can see also for the stiffness part. So there is a tremendous increase in the strength and stiffness, except for the wall with the flexible diaphragm condition. Here there is no strength increment. However, since we have applied the welded wire mesh, its stiffness got increased. But because of the diaphragm condition, the strength hasn't increased. So it means this shows that the boundary condition plays a very important role in the load carrying capacity. Amongst all the retrofitted walls, if you see, the basalt fiber mesh wall have shown the highest increase in strength and also highest increase in the stiffness, because the entire wall has been covered with the reinforcement, whereas in other cases only strips of finite width of reinforcement has been provided. So all the tested walls in the post cracking phase also, if you see, they have shown a very large deformation capacity before the incipient collapse. So this is indicative of a significant energy dissipation capacity, which is a very important and desirable characteristic with regards to the seismic resistance. And here you can also see that the degradation in strength up to 37% has been observed in the initial cycle, which has become relatively gradual during the post-cracking phase. So all the test walls have dissipated a significant amount of energy as demonstrated by the hysteretic loops. Okay, so here you can see that all the hysteretic loops, because of which the higher was the energy dissipation capacity. And if you calculated the damping ratio, which is calculated for each wall, they are founded in the range of 24 to 32%. So we have seen that all the test walls have shown that the techniques using wire mesh, fiber mesh, and fiber reinforced polymer can be used as a promising solution for retrofitting these masonry walls. So the main conclusion is, if you have any existing building, okay, and if you want to strengthen or retrofit it, then we can use the composite materials like wire mesh, textile reinforced mortar, and fiber reinforced polymer very effectively, where not only there is a strength enhancement, there is a large ductility, and there is a large energy absorption capacity is also there. Secondly, either you test the masonry walls in one-way bending or two-way bending, there will be a significant enhancement. The two-way bending is representing a realistic picture and realistic picture about the boundary conditions. So but the thing is, if you want to design any new unreinforced masonry building, let's say a 2 or 3 story building, it may be a low cost housing buildings. In such cases, you need to make sure that the buildings must have earthquake resistant features. Okay, especially in terms of the connections, all the walls must be tied together in order to have the box behavior, so that the integrity of the walls can be achieved. And the another very important point is that providing the seismic bands. So if you provide the seismic band, the box behavior can be achieved and the buildings will behave satisfactorily, especially in case of the large earthquakes. So we have seen that not only in case of the existing buildings, but also in case of the new buildings, there is an urgent need to design the buildings in such a way that they must be earthquake resistant, because as I said, they are covering almost 75 to 76% of the entire building stock in India. It may be a schools, it may be a colleges, it may be an industrial buildings, it may be a residential constructions or structures of historical importance. So studying this masonry, understanding its behavior is the need of an hour. So this also opens a new area apart from concrete structures and also from the steel structures. The masonry is a gray area where there is a lot of scope in order to do research and to understand the behavior properly, so that as a structural engineer, as a designer, we can design the buildings in order to make it earthquake resistant and safeguard the large existing housing stock, especially in our country. Okay, so with this, I will conclude my presentation, and I'll be very happy if you have any questions. I would like to answer them in detail.
Thank you, sir.
Yeah, thank you so much,
sir,
ma'am.
for this informative session, and you rightly focused on the topic and explained it with great expertise. So now moving forward, I request all the participants to join the discussion and ask questions. They can either raise their hands or they can post questions in the WhatsApp group as well. So please,
So you please read the questions for me, so that
sir,
I
yes.
can address those issues. Yes.
Yes, sir, yes.
Even if you have any fundamental question, any basic thing which you want to ask related to masonry, you're most welcome. It may be related to its compressive strength, it may be related to its bending strength, it may be related to its behavior, one-way bending, two-way bending, it may be anything.
Sir, I have a question.
Yes, please go ahead.
As you have told a lot about different types of reinforcing techniques for this URM. So I
Yes.
just want that if in case if there is a census that India has a very wide building ranges which are unreinforced masonry structures.
Yes.
So which type of particular method, whether it is wire meshing or whether it is basalt fiber meshing or it is basalt fiber
Perfect.
reinforced polymer,
Right.
uh,
Hmm.
which will be bit economical in that particular case?
Okay. No, it's a very important question. See, first of all, before answering this, I want to highlight one thing. Indian Bureau of Indian Standard has only one code, especially for retrofitting of masonry structure. That code is IS 13935, and it came in the year 2009. That code only addresses the welded wire mesh, no other composite material. Okay, because the code people wanted that the box behavior of this building, it means the wall should not act individually during the lateral forces, and therefore there is an urgent need to connect all these walls together in form of a box, so that all the walls, so that there will be a redistribution of the forces from in plane to out of plane and from out of plane to in plane walls. So they have suggested that the wire mesh can be much economical. It is very cheap in nature. Whereas the Italian guidelines, whereas the ASTM codes and the ACI guidelines are not recommending welded wire mesh, because the research on welded wire mesh is very limited. There, the more focus is on the textile reinforced mortar. The word I have used, basalt fiber, it is a material. Okay. The technique is textile reinforced mortar. The textile can be made up of any material. It may be carbon, it may be glass, it may be aramid, it may be basalt, it may be any material. Okay. Either you provide in form of a mesh, or either you may go for the epoxy resin and hardener in form of the textiles. So there are specific and standard guidelines with reference to the Italian and ACI codes, and there are some specific guidelines with respect to the Indian codes. Okay, as far as the economy is concerned, welded wire mesh is much more economical, because these mesh can be easily available in any hardware shop. If you go to any hardware shop, they call this as a chicken mesh, okay, in a layman's language. So you can easily get it. You can simply cut it into required shape and size, and you can apply a layer of a mortar, and based on the guidelines given by the IS 13935, you can follow that protocol and you can retrofit your existing masonry building, especially at the lintel level. The code suggested if your building is located in seismic zone 3, 4, and 5, then what will be the guideline? Okay, what thickness of wire mesh you need to use? What will be the spacing which you need to use? Okay, what will be the height of this lintel band? What type of mortar is basically which you need to use, especially for buildings located in different seismic zones? So that is the guideline. But textile reinforced mortar or using FRP is little a costlier affair, because in India, people are using it, but not extensively. Okay, and if you calculate the relative cost between these three material, so I would rather prefer, or in the presentation also, I have shown you few slides where we have, let's say this slide, where you can see that with the welded wire mesh, you are basically getting the highest strength gain. Okay, same reinforcement ratio, this black bar you can see. Okay, on the right hand side, there is a reinforcement ratio. So if you can see that even providing the same reinforcement ratio, welded wire mesh is basically providing the highest gain in strength as well as the highest energy dissipation capacity. So not only it is economical, but it is also easy to apply. Okay, but there are few problems related to FRP, especially related to the debonding failure mode, where the tensile strength is not fully utilized, and there is also a problem of the application. Okay, since this is an organic matrix, so this needs to be taken care with under a strict supervision. So I will basically rather prefer the welded wire mesh compared to the other two techniques. So the other two, FRP is already been extensively used for concrete structures, but for masonry, FRP is nowadays discouraged. Okay, because of this debonding failure modes. So the current trending technique where the ongoing research is completely focused on TRM, textile reinforced mortar, and this welded wire mesh. I hope it's clear to you.
Okay. One more thing I just want to
Yes.
ask you, that when we apply this particular mesh and then we put the plasters, so we have some sort of things that we have in a terminology that shotcreting. So applying directly by the this particular what to say workers, and applying via the shotcreting technique, which gives a good strength in particular scenario.
Okay. No, that's absolutely correct. See, you are talking about the application of inorganic matrix to the masonry substrate. In the
Yeah.
pictures, what I have shown is the hand layer procedure. Shotcreting is a mechanized procedure. So
Yeah.
the only thing you need to keep in mind is that there must be a proper cover, or there must be a slight gap when you are basically dealing with this wire mesh. Okay, so we usually keep, let's say, a 10 or 11 maximum. A cover needs to be maintained, because what happens is that when you apply a first layer of plaster, that first layer of plaster basically act as a cover to it. Okay, but in case of the spray grouting or in case of the shotcreting, you need to make sure that there is some gap, so that the entire mortar is basically inside. It goes to the porous nature or to the grids of this wire mesh or the fiber mesh. That is the only thing you need to keep in mind. Okay, because when a textile fiber grid has been constructed, they are available in different sizes. It varies from 5 to 100 So if the openings are larger, so either you apply a hand layer procedure or the mechanized procedure, there is no issue. But you just need to make sure that the entire mortar should go beyond the back face of that particular reinforcement, and it should properly adhere to that of the masonry substrate. This is the only thing. But yes, there are a lot of advantages to go for the shotcreting procedure. Okay, when you are applying to this particular mesh, so your question is related to whether the application of mortar using hand layer procedure needs to be followed, or shotcreting is to be applied, or when you are applying the strengthening technique, so shotcreting can be applied or not. So I am little
Yeah.
confused on.
No. The thing is, which gives a higher strength, which gives a higher safety. The applying method, it also depends upon the skilled labors and the applying techniques also, isn't it?
No, I got your point. The only thing which I want to clarify from you is that the shotcreting which you are talking about, is it related to the strengthening reinforcement, or it is related to the plain unreinforced masonry?
No. Strengthening reinforcement.
Okay, fine. Yes, you can go with the shotcreting. No issue at all.
Okay.
Because
you.
hand layer procedure takes a lot of time.
Yeah.
But shotcreting, only thing you need to maintain is the pressure, okay, and the workability of the mix. The mix should not be very rich, it should not be very lean. It should properly, if it is very lean, then the complete mortar will bleed out. Okay, so and if it is too hard, then it is very difficult to give a finished surface, because ultimately the masons has to finish the surface by using the trowels. So your mix should be workable enough, and you can go with the shotcreting. Even you can use the chopped fibers also. In engineered cementitious composite, which I has told you earlier, that you have the mortar, you apply the chopped fibers inside that, and you can have a direct shotcreting. That also increases almost 40 to 50% of the URM strength directly.
Oh, thank you.
Okay.
Thank you, sir. So we have reached at the end of this session.
Okay.
And I want to extend my generous thanks to Dr. P. Pravin Kumar Venkatrao. I want to thank him for his valuable time from the busy schedule to grace this occasion. And I want to thank him for sharing his graceful opinion with us. Thank you so much, sir. And I also thank all the participants for their active participation. Thank you all.
And